Okay, I'm delighted to welcome our first Marine Live speaker of 2024, and that's Dr. Winnie Courtene-Jones from Bangor University. Winnie has been working a lot on microplastics, and she's going to talk to us about some of the problems that they cause and what some of the potential solutions are to this. So, Winnie, over to you.
Brilliant, thank you. Yeah, it's an absolute pleasure to be here with everyone today. Thank you for showing up. And yeah, looking forward to chatting more. So my name's Winnie Courtene-Jones. I'm a lecturer in marine pollution at Bangor University. I'm going to talk about plastic pollution, quantifying the pollution and also identifying some solutions to it. So, as a little bit of background, I'm a biologist, and I've been studying plastics for the last 10 years or so. My research focuses really on three main pillars. In understanding the environmental prevalence, so the quantities in the environment, the fate and behaviour of those in the environment, so where does plastic go, how does it interact, and then also the impacts on ecosystems and species. Really, these three pillars sort of feed up to overall understanding and informing on the environmental risk of plastics and microplastics, and establishing what effective solutions or interventions might be. I work across marine and terrestrial environments, and in addition to being a lecturer here, I'm also an active member of the Scientists' Coalition for an Effective Plastics Treaty. And I'll talk a little bit more about that a little bit later on. Okay, but enough about me, but I thought it might be nice just to give you a bit of an overview of why I'm here talking to you today. What are we actually going to cover in this talk? Well, I'll give a bit of a background and context about plastic pollution before moving on to the environmental prevalence, effects of plastics, and then an outlook on some solutions and the policy landscape. So when we talk about plastic, what do we actually mean? And that might sound really obvious, considering that we interact with plastics on a daily basis, but it's actually a really complex material. Plastic is derived of what we call monomers and polymers. These are sort of the building blocks. So you can think of a monomer as an individual unit, one brick, and you line those up to form a polymer of these many repeating units. So now we're starting to sort of build the wall of our house. We've got this long chain. But onto that, we add a range of other products, chemicals, additives. In fact, over 12,000 different chemicals are associated with plastics. And these might have different properties. So they might be added because they give the plastic a nice colour, or because they have beneficial characteristics, like they increase the durability or the flow. They might have antimicrobial or anti-static properties. We also have other intentionally added substances, things that were there due to the manufacture of the plastic, and also non-intentionally added substances. And these might be things like solvents or catalysts and other materials left over, sort of residues on the plastic from that production process, or from recycling, if we're thinking about recycling that plastic into another product. So this is a really complex material that we call plastic. And I'm sure you may have seen things like this before, this increase in plastics production over the years. So you can see in that figure there, the bars, the coloured bars increasing over those decades from the 1980s all the way up to present day. And it's now estimated that there's over 460 million tonnes of plastics produced annually. Here you can see it divided by the different sectors. So we've got packaging, for example, in blue as the major sector using plastics, but a range of others as well. Vehicles, textiles, we use it in construction and in packaging products. In the bottom right, I find this a very interesting picture. This was published in a magazine, Life magazine, in the 1950s. And this is the real start of this mass plastic production, where we've taken the material and made it cheap enough and versatile in a range of different products. So this image shows a modern family, and instead of, cooking and having to wash up afterwards, we've got all of our foods coming in plastic that we can just microwave, eat, and then dispose of that once we're done. And it's this type of what we call a linear chain, where we're taking a product, using it, and then disposing of it, that's part of the problem. Because plastic is highly durable, but we're using it in very short-lived applications. So this is not a problem necessarily of the material of the plastic. We've designed it to be durable, but it's our relationship of how we're interacting and using the plastic. And we now produce far more plastic than waste management facilities can cope with. As I said, 460 million tons of plastics produced annually. It's estimated there are over half, so 60% of all of that plastic that's ever been made is now in the landfill or disposed of in the environment. So that's substantial quantities that are out in the environment. And once it gets there, of course, it can break down into small pieces. And this can be distributed because it is lightweight and durable. It can be distributed around the environment, located from mountaintops, freshwater, lakes, soils, and even down to the deep sea floor. So what are the sources of this plastic? And I mentioned the term microplastic a minute ago. What is a microplastic? This is a collective term that's used to describe a really complex and diverse mixture of different plastic particles that are typically less than 5 millimeters in size. Now, these can arise from direct manufacture. So we can make plastics to be of that very small size. You can see there on the figure, personal care products and plastic pellets, those first two bars. They're intentionally made to be of small size. We also have microplastics that can be generated through the use and the wear of larger plastic items, things like tires or synthetic textiles, and also paint. These can fragment and form small particles just in their everyday use. And finally, we also have plastics, microplastics that arise from the fragmentation of larger plastic items once they're in our environment. So there's a range of different sources, and there you can see the relative contribution of each of those types. Of course, this isn't an exhaustive list of every type of plastic and microplastic. We also have others that arise, for example, degradation of fishing nets and ropes, plastics used in sports pitches, and even mechanical recycling can generate microplastics. So there's a real diversity of sources of plastic. And there's substantial evidence now over the past 2 decades. Hundreds of papers have been published documenting the really widespread occurrence of microplastics in the environment. Like I just said, we've seen them and we can detect them from mountaintops through to lakes and rivers, beaches and shorelines, all the way through the water column and down to the deep sea floor. We also find that these are ingested by organisms, from invertebrates right down at the base of the food chain through to top predators like seabirds, whales, and other predatory species. And the figure on your screen just shows a range of different environments that we've documented microplastics in, and some estimates there on the different quantities if you're interested in that. If not, don't worry about the numbers. This just illustrates the range of different environments that we've got data showing the widespread occurrence of microplastics. But how do these microplastic particles actually enter the environment? That's a question I get asked quite a lot. Of course, there are things like littering and mismanaged waste, but our everyday actions can also generate microplastics that go out into the environment. So I mentioned previously that one source of microplastics is from tyres. Well, stormwater runoff from our roads can carry these particles down through storm drains and out into the ocean or into waterways. And similarly for textile fibres, as we wash our clothing, small fibres come out and get carried down through the wastewater and are emitted out through wastewater discharge. We also have some plastics that are used directly in the environment. Agricultural mulch films, for example, are used in, as the name suggests, in agricultural settings. So they're applied directly onto the land and they can stay there at the end of their life. Likewise with encapsulated fertilizers. So there's a broad range of different ways that we can introduce either intentionally or perhaps unintentionally plastics into our environment. And then these are transported really long distances. This shows ocean currents connecting our planet. So you can see on the figure the blue arrows that show just broad scale ocean circulation. And over the top, we've got different colours indicating sort of the density or quantity of plastics within these different ocean basins, going from pale colours where there's relatively few microplastics, all the way up through to those dark reds indicating sort of hotspots out in the centres of each of those ocean basins. But ocean currents, of course, can connect our entire planet and move plastics over really long ranges. And this widespread movement of microplastics across the ocean can really pose challenges when we're trying to reduce plastic pollution. And therefore, some of my work is trying to understand that movement because it has an importance to understanding the source and the distribution, but also where we can introduce intervention points to reduce that flow of waste out into the sea. So here I just want to illustrate some of my work that looks at the quantities of microplastics and how they differ spatially and what factors influence those. This is a study from the Southern Caribbean, but I think it really nicely shows sort of the interconnections and the complex nature of trying to tackle plastic pollution. So in this study, myself and colleagues integrated different sampling techniques. So we carried out water sampling at the surface, at the subsurface, so some meters below the surface of the ocean, and also grab sampling to look at sediments. And in each of those, we characterised and quantified the amount of plastic pollution, of small microplastics, in each of those different parts of the environment. We coupled this with hydrodynamic ocean modelling, which looks at the movement and the distribution of plastics within the sea. And we also added in land-based litter assessments, along with an analysis of regional and Caribbean wide-scale policy and waste management facilities to try and really get a more holistic understanding of that region and the flow and movement of microplastics. And what did we find? Well, at the time that we carried out this work and at the time of the study was published, we identified that there were 20 different Caribbean nations that have some form of legislation or ban in place against some type of plastic. And this was mainly, again, these interventions were mainly limiting the use of plastic bags or also polystyrene items, styrofoam takeaway containers, for example. And whilst we found really low levels of these types of litter in our land-based assessment, so we can say that those interventions are quite effective at reducing the litter in the streets and on the shore, in the street, sorry. We still found those as plastic particles in the territorial waters. So within that country's water, despite there being a ban on land, we were still finding styrofoam fragments and small fragments of polyethylene bags as microplastics. When we carried out ocean modelling, what we see is that there's movement of the plastic. So on the figure that's just popped up now, you can see different coloured triangles and dots. So the triangles are where we actually went and sampled for plastic, and the points show backtracked in time where that plastic may have come from. And particularly for those red points, you can see that the broader North Atlantic Ocean, so to the right of that figure, are being carried in by ocean currents and are washing up on those outer Caribbean countries. So because of these prevailing ocean dynamics and microplastics being able to be transported really long distances, this has the potential to undermine those local policies that are put in place. So despite local action, we're still seeing the distribution of plastics. So what we can say here is that, even if there's an action or a policy being taken in one localized area, this doesn't necessarily translate to less plastic pollution and less washing up from distant sources on a particular country's shorelines. And this really underscores the importance of the broader environment and the need for international and collaborative strategies to actually bring about effective reductions in plastic pollution in the environment. So, as I've said, plastics and microplastics are really widespread, and they can be transported by ocean currents over really, really long distances. There's more and more evidence coming out of the detrimental impacts that plastic has, both on organisms, the environment, but also on social and economic aspects as well. I'm not going into a huge amount of detail on the social and economic consequences, but just as one example, or a few examples here, chemicals within that plastic can be released throughout the lifetime. So the lifetime of the plastics from its manufacture, through its use, right up to disposal. And we, as humans, are interacting with the plastic and being exposed to those. There's also implications on greenhouse gas emission through the production of plastic, and also the trade and shipment of plastic waste between different countries puts immense pressure, often on developing nations, which don't necessarily have infrastructure in place to effectively or safely deal with this plastic waste. But the majority of my research and my background is sort of focused on understanding the environmental impact of those plastics in the environment. And we know now there's emerging evidence and more studies that are documenting plastics detrimentally interacting with hundreds or thousands even of different species. Organisms right from the base of our food chain, like on the image on the right of your screen, which shows one large microplastic fragment there in the center, and also a little fiber that may have come from textiles, so our clothing, and some zooplankton around it. So these organisms right at the very base of our food chain, all the way up through to the top predators, for example, the seabird here. And you may have seen these emotive images showing, birds entangled in plastic debris, which of course can lead to physical harm. But interactions and ingestion of microplastics and the associated chemicals within that plastic are also shown to impact the growth, the survival, the reproduction, metabolic activity of a range of different species. With this comes another area that I've been focused on over the last few years, and that is something we call alternative plastics, or bio-based and biodegradable plastics. Now, these are not new. They've been around for a few centuries, but we're seeing more production and more attention around these different types of plastics, partly because of the concern and scientific evidence illustrating the pervasiveness of more conventional plastics in the environment. So, what is a bio-based and a biodegradable plastic? I'm sure that's what you're asking me, or that's what you're thinking to yourself. So I mentioned at the very beginning, we have a plastic that's made up of these units, these monomers and polymers. Now, these are chains of carbon. And traditionally, the carbon has come from oil. So we call those fossil-based plastics, or I termed them conventional plastic. So bio-based plastics are where that carbon has come from bacteria, plant matter, algae. So the carbon has come from a sort of renewable or bio-based source. Now, biodegradable plastics sit right in the middle of that. They straddle both. It can be a fossil-based plastic and it can be a bio-based plastic. But it has these properties of biodegradability. And what that means is, under the right conditions, this plastic can be biodegraded by microorganisms, so it can be broken down into its elements, water, gas, so back to carbon, with the aid of microorganisms. We also have a small subset, which is called compostable plastic, that can be industrially composted at high temperatures, again, to be converted back from a plastic back into its individual components. Now, bio-based and biodegradable plastics are often promoted as environmentally friendly compared to their petrochemical counterparts. But is this really the case? And that's sort of what some of my research has been focusing on over the last few years. Now, I might add here that there's a range of different applications of bio-based and biodegradable plastics. So we're seeing them more and more in everyday use. Things like flexible packaging, textile materials, agricultural products, horticultural products as well. You may not actually know that you've got a bio-based or a biodegradable plastic. If you're just holding it, they don't look any different necessarily. So I mentioned that a biodegradable plastic means, in theory, that it can be degraded back into its individual molecular components. But the rate at which that happens varies considerably according to two main factors. So firstly, the type of plastic and its composition, its chemical profile, but also according to the environmental conditions that it finds itself in, or that it's disposed of. So here you can see 4 different environments: a nice river, the ocean, a coastline, and an agricultural field. Well, the temperature, the oxygen, the humidity, the microorganisms that are present within just those 4 different environments vary dramatically, let alone when we factor in global scale changes, so a tropical region compared to a temperate region. And it's these factors that are helping to stimulate the breakdown of the plastic. So of course, depending on where that plastic ends up, the rate at which it biodegrades will dramatically differ. And there are considerable knowledge gaps around this. So there's still many unanswered questions about this rate and which factors are really influencing that biodegradation and how long a plastic may persist in different conditions, as well, of course, as the environmental effect that has. So just like a traditional conventional plastic, there's a range of different chemicals added into those biodegradables. So how do those that may be released as the plastic is degrading, how might them, along with the plastic itself, influence the environment and the organisms? And that's what I've been trying to work on with colleagues and students over the past few years. So what are the ecological effects of these biodegradable plastics, and how do they compare to conventional plastic? Before we start promoting one type of plastic over another, we need to understand these different processes. I'm not going into a huge amount of detail now, just because of some time constraints, and I do want time for some questions at the end. But myself, along with colleagues, have been working to try and address some of these questions. So looking at a range of different biodegradable plastics used in textiles, used in tea bags. I don't know if many of you know that a tea bag has a layer of plastic over the surface so that it can be heat sealed, closed, and keep the tea inside it. So now these are being made of bio-based plastic. So we've been looking at those, textiles, like I just said, tree guards, and also agricultural mulching films, and understanding the effects that these have on a range of different marine and terrestrial species, as well as on ecosystem health more broadly, such as the effect on soil functioning. We've had some published studies out that I'm just indicating there at the bottom. And I'm not going into detail or presenting data on these today. Those papers are open access, or there's a time for some questions at the end. But broadly, what we've shown is that organisms, and what we've done is expose these different organisms and ecosystems to plastic particles, either biodegradable or conventional, and we've measured the responses of organisms to those so that we can compare the effect. And what we find are a range of different effects on the survival, the growth, the reproduction, and the organism health and behaviour that are varying according to the type of bio-based and biodegradable plastic, but that are broadly comparable, and in some cases actually more pronounced than conventional plastic. So we see similar or perhaps more severe impacts of these bio-based biodegradable plastics on organisms than a conventional plastic. And this just really underscores that necessity of testing these products before we start widespread adoption and rolling these out to even more applications. We need to be sure that we're actually, moving to a better alternative, not just switching problems. We might find ourselves in a situation where we've just moved materials and we end up with a range of unintended consequences. So we need thorough evaluation of these materials, just like conventional plastics. So sort of drawing a little bit to a close now and just wrapping up, what we've seen is the scientific evidence clearly shows that there's a range of different sources of plastic. These are widespread in the environment and are moved by natural processes, ocean circulation, for example. We've got widespread toxicological effects on aquatic and terrestrial species right through our food chain. And there's emerging evidence also indicating that microplastics are in the food that we eat, water that we're drinking, and the air that we're breathing. And they can also have impacts associated on human health and well-being, which I've not gone into detail on today. And as I just illustrated, we need to take care if we're switching from one type of plastic to another, that this doesn't bring regrettable substitutions and unintended consequences. So we find ourselves now in a time where there's a body of scientific evidence, and that's really helping to drive pressure, along with media coverage, social drivers of change, and individual action are really helping to drive forwards policy outcomes. So we're seeing more solutions or interventions, policies on different single-use products, and different sort of local and national regulations. But what we need is large-scale, collective and international action if we're actually to make effective progress in reducing plastic pollution. So unless we take this action, if we just carry on under business as usual scenario, so if we just stay exactly as we are now, the amount of plastics and microplastics in the environment may increase. So from what's currently estimated going into the environment, 10 to 40 million tonnes per year, this could double in the next 20 years. Really underscoring that point that we need large-scale international collective effort. So we now find ourselves at this exciting time where there's a tangible opportunity for action. And this comes with the UN Global Plastics Treaty. This treaty has been under negotiation for the last few years by over 170 different UN member states. And it's anticipated that 2025 is the year. The negotiations should conclude later this year. So we're reaching the sort of climax point of this negotiation and all of this effort and work that's been going on behind the scenes. But of course, it's still anything to play for. The text has been, there's been so many iterations of the text, and each of these member countries comes from a different standpoint, maybe with their own political agendas and wills, which are influencing these discussions. So really now is a time, now it's really essential that those countries that are pushing for ambitious, effective treaty remain strong and really leverage their collective voice and are guided by what the scientific evidence is showing. Now, I briefly mentioned the Scientists' Coalition for an Effective Plastics Treaty at the beginning of this talk. And this is a network of over 400 international, multidisciplinary and independent scientists that have been working over these years behind the scenes, working really closely with negotiators and member states to provide science to those negotiators. To do that, we produce policy briefs and work very closely, having dialogues with any member state who needs some scientific expertise. We also attend all of the different negotiation meetings, and I lead several working groups within the coalition to sort of further that understanding progress of science. Well, science to policy, I should say. And just wrapping up here, last couple of slides about where I think the future is going and how what are those effective solutions? Well, as with every complex problem, there's no one single action that will suffice. There's no silver bullet. We need a collective effort across what we term the plastics life cycle. And you can see that illustration there that shows the full plastic life cycle. So when we think about plastic, we need to consider all the way back from that resource extraction, whether that carbon is coming from oil or from a bio-based feedstock, through the production, the manufacture, the transport and the trade of that plastic, right through to its use, waste, recycling and remediation from the environment. And it's taking this broad life cycle approach that is really necessary to protect human health, society, and the environment. There's often a focus on end of life, so recycling, right down near the end of that list. Global plastic recycling rates are only around 10%, yet this is what's receiving a lot of attention and also a lot of investment. But it's much cheaper and far more effective to deal with plastic pollution and plastics by implementing upstream measures. So moving further up that list back towards the production and the manufacture. So here we can reduce overall production, simplify products, simplify chemicals that are going into them, rather than relying on trying to clear it up from the environment, which is much more complicated, challenging, and costly. So really, we need to be looking across this life cycle and at interventions that focus near the start. Briefly, 6 main ways that science can guide this treaty process and support solutions. So a reduction of primary plastic production, phasing out non-essential chemicals, materials and products, and where plastic is deemed as having a critical function for health, safety and society, consider an alternative, but ensure that alternative is also safe and sustainable. We can implement restrictions on plastic chemicals and apply harmonised safety, sustainability criteria to plastics, alternative plastics, and also the chemicals that are within them. We need mandates on transparency and traceability criteria to help protect the environment and human health, but also provide incentives such as financial mechanisms and technological cooperation to support changes, and ensure that human rights are really centred within this to ensure that there's an equitable and just transition for those people that are really most affected by plastics. Finally, going across all of these, we need an independent science policy body composed of diverse experts, knowledge holders, and rights holders to ensure that there's there is a no conflict of interest and that the treaty gets implemented effectively. Just highlighting a few wonderful people that I've been privileged enough to work with that are all passionate, optimistic, and working hard to drive this change forwards. The pursuit of science is not an independent endeavour, but relies on so many different people all working together to create this positive change. And with that, I want to thank you and very much for your attention. And I do hope that we have a few minutes for some questions. So I'll end now, and then we can stop sharing and come back for some questions.